Work and energy, or the work-energy conservation theory, part 1. How to diagram energy. I'm going to teach you a way of doing energy diagrams, where in short, the idea is the decrease of one form of energy is accounted for by the increase of another form of energy. This is energy conservation. Minus delta E1, the change or loss of one form of energy, by energy conservation must be accounted for by the change of another form or other forms of energy, such as loss of E1 is the gained by a second form of energy, E2. Now recall from an earlier video on kinematics, this fellow here dropped the ball, and looking at the motion diagram of a ball, as it's falling, it's in non-uniform motion as it's increasing its speed. Well, now we're going to use energy conservation to examine this non-uniform motion of falling objects. Y initial is at some height, Y final, we'll say, is at 0. Displacement is negative. As this object is falling, it's gaining speed. You've learned that gravitational energy, PEG, is equal to mgy, a mass, thanks to gravity, at some particular height from the center of the Earth. Whatever our arbitrary reference is for our height gives us an arbitrary value of our gravitational energy. More mass, more gravitational energy. Greater gravity, more gravitational energy. Greater value of y, greater altitude, greater height from the center of the Earth, more gravitational energy. More potential for more motion. But as something falls or gets displaced, there's a delta y, which means we're changing the gravitational energy. It's the delta, as always in physics, that's important. The change in height, the change in gravitational energy. It's the change in gravitational energy, and only the changes that can be equated in energy conservation. The loss or the gain in gravitational energy is what's equated with loss or gain of other forms of energy. So this change in gravitational energy, let's keep it down here, and in its formula, mg delta y. Well, we know the initial speed is 0. We drop it. The final speed right before impact is Vmax. So as we lose height, we gain speed from initial to final. So gaining speed is a gain in kinetic energy. You've learned that kinetic energy is dependent on the mass. The more massive the object is, the more kinetic energy it must have. Or a more massive object must be given more kinetic energy to go at a particular speed v. So kinetic energy is 1/2 mv squared. That speed is important. It gets squared. Kinetic energy is greatly dependent on the speed. But if we're changing speed, we're changing kinetic energy. So let's put that down here. Increasing kinetic energy as we're decreasing gravitational energy. No coincidence. They are equated. The loss of gravitational energy is the gain in kinetic energy. One of the formulas, mg delta y is equal to 1/2 m delta v squared. We observe losses of height and gains of speed. These observables indicate that there are changes in energy forms. They're observable. The loss of height indicates a loss in gravitational energy. So we're losing this form of energy. This loss of energy, this form of energy must be accounted for. This form of energy must go somewhere else in a sense. We don't really know what energy is. In a sense, it's just a number. But I'm diagramming a way to think about energy. The same way we diagram forces in force diagrams. And we keep track of momentum, and momentum tables are meant by playing momentum Sudoku. And we have motion diagrams to keep track of, to see subtleties of changes of motion. We'll think about energy as a thing, like a substance, as if it's a fuel draining out of one form. This container is a form of energy. It's in a PE container, or like a tank of energy. So we have energy in this container, or this form, and we're increasing our kinetic energy at the loss, at the expense of the decrease in gravitational energy. Energy is being transferred from gravitational form to kinetic form. It's like a fuel is draining out of one tank, the potential tank, into the speed tank. So the loss of gravitational energy is the gain in kinetic energy. We're watching the transfer from one form to another. This transfer, this loss in one form and the gain of the other, gives us the signs of energy conservation. Our energy conservation equation, we can diagram to see the signs, the loss of one and going to the gain of the other. We see now our formulas are all set up with the proper signs. Our energy conservation equation there. This was done by our indicators of our observables: decreases in height, negative delta y, increases in speed. V initial, V final tells us the increase in the signs and the decreases of the respective energies. And we see the negative displacement and the negative gravitational energy give us a positive overall value of energy on the left, and the positive overall change in kinetic energy on the right. So our signs work out. Again, the observables from Y initial to Y final, and the observables indicate V initial to V final, the changes in the signs of energy, represented simply by the deltas, the changes of energy, the transfers of energy, put us in a proper energy conservation equation. And now, with our formulas for gravitational kinetic energy, we're all set to go with a proper energy conservation equation with the correct signs, and we can solve for what's ever asked for, such as finding the final speed. Let's cross out those masses, put the 2 on one side and get rid of the half. Left of 2g delta y is equal to the change in speed squared. This is Galileo's principle that we discovered earlier. The speed change is governed solely by the fall. This is a free fall equation. The height it falls, thanks to gravity, determines the speed that it gains, or the speed change. We've used energy conservation. By no coincidence, it came up with the same result that Galileo found using kinematics. Long before energy and Newton forces, he observed as things falling thanks to gravity and free fall gain speed. Energy conservation has just showed us another analysis to get that same result. But you've also seen this equation before. Gravity is gravitational acceleration. The displacement, 2AD, relates to V final squared minus V initial squared. This was one of your 4 kinematic equations, usually listed as your 3rd kinematic equation. That must mean delta V squared is V final squared minus V initial squared. Delta V squared is not the same thing as V final minus V initial squared. It's not the square of the difference. For instance, 100 minus 90 squared is the same thing as 10 minus 0 squared. But let's say you get hit by a car at 100 miles an hour, and the car only slows down from the hit to 90 miles an hour. If we square that loss of speed, accounting for the kinetic energy that the car lost, which got transferred to you, it'd be the same thing as getting hit by a car at 10 miles an hour, and the hit stops the car. The square of the difference in speeds relates to the square of the energy that was transferred to you, lost from the car. There'd be no difference getting hit by a car at 10 miles an hour or 100 miles an hour and losing only 10 miles of speed. But you know you'd rather get hit by a car at 10 miles an hour than 100 miles an hour, because there is a great difference between those two speeds. It's 100 squared minus 90 squared, which is not the same thing as 10 squared minus 0 squared. It's nowhere close. It's kinetic energy final minus kinetic energy initial, which means it's V final squared minus V initial squared. Do not make that mistake. Delta V squared is V final squared minus V initial squared. And there's your kinematic equation again. Now what if instead our initial condition is right after the floor, as if it's bounced? The ball is now fallen and then returns on a bounce. So initial is right at the floor on its way up, and the final is back at the hand. So going from up initial to final, we're increasing y. Therefore, we're increasing gravitational energy. And going from initial to final, from floor to hand, we're decreasing speed. Initial speed is the maximum, and the final speed is right before returning to the same height. It's at the top of its motion, so it has no speed. Otherwise, it would be at the top of its motion. So that means there's a gain in potential energy and a loss in kinetic energy. Our energy conservation equations and tanks are all exactly the same. We just have to flip the signs. What this says is the energy conservation works both ways. The kinetic energy was gained by the loss in gravitational energy, and then after the bounce, we see energy conservation in play. The loss in kinetic energy is accounted for by the gain in gravitational energy. And as it bounces on over and over again, it's energy conservation. Gravitational energy drains away into kinetic energy. Kinetic energy drains back into gravitational energy over and over and over again. If there are no external losses from the bounce, from friction and drag of the air, the ball would bounce back and forth to the same locations within the same dynamics, the same speeds forever. One tank would fill up as the other one would drain. Again, we simply just switch our signs, initial greater than final. We'd see our energy conservation equation balances the same way with the same proper signs. Transfer just goes the other direction. This is like the bar charts in your text, going up and down over time. So in this case, the loss of one form of energy is the gain of the other. And that's the whole point of diagramming it, to show the energy gains, the energy losses of different forms, and keep them accounted for. So the change in 1 plus the change in 2 equates to 0. The transfers are accounted for. There's no change in total. That must mean the total is a constant. And that's the heart of energy conservation. E total is a constant. E total is E1 plus E2. This constant, this energy total, this total energy never changes. Total energy is conserved in this situation. And so if we change the constant, we get 0. So the loss of 1 is the gain of 2, and vice versa. Now let's say you drop the ball and it compresses a spring. There's a spring being compressed. The ball falls initially. Final is the compressed spring. The ball crushes the spring to make a final situation of compressed spring. We have an equilibrium length of a spring, and then it gets crushed. L equilibrium, the length of the spring, and it gets crushed by a certain amount, a delta L, the amount the spring is compressed. So again, initial conditions is height h. Final, let's say, is 0 in terms of height. The initial is a drop, so initial speed is 0. The final speed is also 0 in crushing it. So there's no change in velocity, therefore there's no change in kinetic energy. So we lost gravitational energy, but we didn't gain kinetic energy. Again, the initial speed is 0. The final speed, the ball is no longer moving. It's to compress the spring all the way. So the initial speed and the final speed are the same. There's no change, therefore there's no change in kinetic energy. So the loss of gravitational energy between initial and final must have been accounted for by some other energy form. Some other container of energy is taking up that energy transfer. Some other tank of energy that's not kinetic, that's taking up that loss in gravitational energy. What is it? Well, the length of the spring has been changed. That indicates, we observe this indicates there's another form of energy being evolved. You know, if you crush a spring, it takes energy, effort, to crush a spring. We feel we're putting energy into the spring. The spring has potential to snap back and release its energy. That's potential energy of a spring. So we just increase the potential energy PE spring by compressing that spring. The fall, the loss of gravitational energy, ultimately went into compressing a spring, making a spring taking the energy that the gravity lost from that fall, meaning the spring got compressed by an object falling. So this is a loss in PE gravity as the gain in PE spring. Sans delta minus the gravitational energy is the increase in potential energy of the spring. Two forms of potential energy. In formulas, the spring energy, as you learned, is 1/2 K, the spring constant. The spring constant is the strength of the material of the spring, how tightly wound it is. Weak spring versus strong spring, for example. And delta L, how much you've changed the length of the spring. Delta L, how much in this case the spring has been compressed. It goes as square as delta L. It's very important how much the spring has been changed. Compress the spring 2 centimeters, and then compress the spring another 2 centimeters. Well, double the compression of the spring takes 4 times the energy. Triple the compression of the spring, triple squared, takes 9 times the energy. So we rearrange our formulas, and we can solve for how much the spring gets compressed, depending on the height of the ball that's dropped, delta Y, and the strength of the spring, K. Work. Work is defined as a change in energy, a delta E. If the energy increases, it's positive work. If energy decreases of some form, that would be negative work, such as if it's a loss of speed, a loss of kinetic energy, that's negative kinetic energy, negative delta KE, let's say from the negative work of friction. Friction slows things down, so it's a losing kinetic energy. Something gains gravitational energy, say from a spring shoots, say, the ball up. The spring did work to shoot the ball up to gain gravitational energy, positive delta PE gravity from the work of the spring, adding energy to the gravitational tank or the gravitational form by lifting it up. Whereas the work of friction slowed something down, it decreased, negative, minus the amount of kinetic energy from the work of friction, for example. So if one form of energy is decreasing, the tank is decreasing, container is decreasing, it's losing energy, so that would be a negative delta E or negative work. It's losing energy, that tank is draining away, that energy is going somewhere else. That's a negative work or a loss of energy, negative work meaning an output. That energy is being outputted, being lost in that form. So work is going out or outputted, it's negative work. Instead, we have positive work, that's like an input. That means a form of energy is gaining. So an increase of one form of energy. Energy is gaining in some tank or increasing. Something must have been inputted. Positive work. But we know if some form of energy increases, some other form of energy has to decrease. So the negative work of one form is the positive work on another form, where the output of one energy is negative work, which can be the input in a different form of energy, a positive work. So work is just diagramming or discussing the transfer, the process, the change of the energy. Work is also related to a force times distance, meaning we have to force things over some displacement, over some distance. We have to force things in an interaction. They have to be forced to change their forms of energy. Things change energy by being forced to go from one form, one container, to another. We'll deal more with force times distance as a work in a future video. Such as, example, we can increase something's speed if we force it in the same direction it's moving. We apply a force, we push something along the direction it's moving. This mass is being displaced to the right. We apply a force, a net force, to push the mass to the right. We're increasing the mass speed. It's moving to the right, we're pushing it to the right to increase its speed. That's positive work as we're increasing its kinetic energy. The force and the displacement are the same direction. Whether they're both to the right or both to the left, if they have the same direction, they'll have the same sign, which will give us a positive change in the kinetic energy. We're putting energy in to speed up this mass, to increase its kinetic energy. If the force is opposing it, you know it's slowing down. So the force is opposite the direction. The force is opposite the displacement, so it has opposite signs, such as a negative force and a positive displacement gives us a negative kinetic energy. A positive force and negative displacement would also give us opposite signs, negative kinetic energy. In this case, we're taking energy out of the kinetic energy form. Kinetic energy is being drained away. We're taking speed energy out of this mass by forcing against its motion. So this would be negative work. This, of course, is the net force we're talking about. The net force is the one that's involved with changing the motion, the one that's involved with the acceleration. And I only can put in one value of force into this equation. I have a changing force, I have to integrate. I can't use this equation directly. So this is the net average force that goes into this equation. If my force is changing, I have a changing force, then I want to integrate that change over the distance that I'm applying that force. And that'll give me the total work. We'll deal more with work as an integral and work relating to force times distance in a future video.